Okay, so let's talk about the radio, the interferometry. So imagine that actually we are operating the two radio dishes. Okay, so that radio dish, that actually that the one at here, and then second. So looking at the same source, so that actually it is separated on the ground by certain the distance away, and it is actually just the telescope steered into the same the object, so that actually that up until this that dashed line, that the incoming the wave from the source is actually perfectly in phase. Okay, but because of the phase the length difference, path length difference to reach to the second the telescope, because of the path length difference, when you actually mix this signal together from the two telescopes, there's a phase difference, and then this phase difference is actually causing the interference pattern. Okay, so and then also there actually this the path length difference is actually also proportional to, I think, not the proportional, it is actually the dependent on the source position in the heavenly sky. Imagine that for any given source is actually rising from the east, and the transit at the south point, the meridian, and then set at the on the west. So when we actually the tracking this object with the two radio telescope, its effective path length difference is actually changing over time, right? So because of this, the interference pattern, frequency, and an amplitude are also changing as a function of time while they're actually we are observing this single object by using these two the telescope array. So this is actually the so-called the visibility power. So this is the interference patterns power, and it is actually showing that actually this so-called the fringe pattern is changing as a function of time and achieving the highest the frequency and the maximum power when it is actually just the transiting, so that this fringe pattern is actually showing having an information of that actually that what this source the size can be, and it tells about the characteristics of the source the signal. Okay? But the contrary to the single dish observation of actually seeing the object. Okay, so when the single dish is actually seeing the object, it is actually producing the through the focusing mechanism, it is actually producing the diffraction the pattern. This is called the Airy pattern, right? For the given the aperture size, and this is limited by as the aforementioned that diffraction limit, right? But when we actually use these two telescope, what we are actually seeing is actually the effective our effective aperture that actually determining the diffraction limit is actually basically this projected the path length difference between these two the telescope the separation. Okay, so by the putting the separating the two radio dishes further apart, we can actually increasing the effective the aperture size of the interferometric mode of two telescope operation. So the diffraction limit is actually just defined by the lambda over d, right? So for the given fixed the frequency of the observation, we are basically effectively increasing the diameter, or just the aperture size of the telescope by separating these two telescopes further apart. So imagine that actually that the for the single dish, the primary mirror is actually have solid 100% the solid the reflecting surface inside of the circle. In the interferometry mode, the two telescope is separated by this amount, and actually this whole on the primary mirror is empty except this two point that covered by these two telescope. So yet still there actually effective the diameter of this imaginary two telescope large, the combined mode of telescope is actually still this separation of d. So that's hence the beauty of that actually just using this the two more than two telescope, especially typically used in the radio frequency, because interferometry pattern need to actually just disentangle this fringe pattern, and then we need to actually dissect the one waves in the fringe patterns from another the packet. So that means actually we need our current technology is actually just allowing only that actually that handling maybe some several hundred megahertz the fringe patterns, and we can isolate one of these fringe pattern amplitude. But as we go to the higher and higher frequency, we are actually just not being able to actually control this fringe. So that means actually this interferometry is actually working fine at the radio frequency, but actually we are barely being able to actually just tapping into this the fringe, the controlling at the higher frequency, such as infrared. Mid-infrared is actually already doable. Near-infrared is actually being pioneered and then experimented, and optical has been tried and then not so much of actually success there. So, but basically we are actually just using this interferometry pattern in radio frequency that predominantly, because that the radio dishes actually, even if the dishes are really large, it is far from the diffraction limited. So I mean that actually the diffraction limit is actually so much larger, so that actually we cannot actually really see the fine structure in the radio, the frequency of the celestial source using a single dish telescope. So that actually to increase the spatial resolution and then increase the diffraction limit, the angular resolution, we are actually using the more than two telescope in an array interferometry mode. But this separation, okay, so this effective size that actually defining this artificial larger the telescope, the D, is actually effective separation of these two telescope, and effective the separation of two telescope is the separation on the ground projected toward the projected onto the sky plane toward the celestial object. So that is this separation. The size is the effective the separation D. And then imagine that actually this D is actually changing over time while we are actually just tracking a single the celestial object, as it actually just rise from the east and then setting at the west, right? So that actually the dish interferometer only gives information on this projected the separation, which is along the east and west direction. East and west direction is basically only the right ascension the part. So to get the 2D information, so that means actually imagine that actually this is the solid mirror and this is the two telescope in the interferometry mode. To get full the 2D information, we need to fill this empty space as much as we can. One way to do is actually that while we are actually tracking the given telescope, this effective way the separation is changing, so that actually that over time that actually that the single the dish is actually covering about that much, and then another dish is actually covering that much. Imagine that actually we are adding additional telescope, additional radio dishes strategically that are actually arranged so that actually to fill this gap. Okay, that means actually this solid mirror is actually will produce perfect error ring diffraction limit, right? But these the kind of just the complicated the partially occupied the primary mirror reflection surface will produce very strange, very complex error pattern. Okay, and this the complex error pattern that formed by the array of radio telescope, and then from this complex the point spread function that actually the retrieving the true the source structure is actually just known as aperture synthesis. Okay, aperture synthesis in radio astronomy. So the typical the radio telescope arrays are actually in a Y the configuration, such as like the very large array in New Mexico. This is the 27 antennas actually with each of them is 25 meters size, and its separation and its distribution pattern can be adjusted. Maximum baseline of the one antenna to the maximum separation of these two antennae in a the deployed pattern is 36 kilometers, and it is operating at right in the middle of the radio frequency. And this is the close-in view of the very large array in New Mexico, and this has at most about up to 40 kilometers of baseline. And that actually, for the given radio frequency, it actually they provide decent several arcsecond the resolutions at the high frequency. Okay, no, at the low in the middle of the radio frequency. But what if that actually we want to really this being able to see that actually sub-arcsecond very fine structure of, for example, they're actually forming planetary systems in radio frequency. This 40 kilometer baseline is nowhere enough. So that's why they're actually astronomers actually kind of just they're starting the international consortium. They're actually just combining the radio dishes separate they situated in the many different the island or continent that actually we are the combining the beams. So that actually imagine that actually one on the Puerto Rico, for example. So no, actually so one in the actually just in the one in the Atlantic, and then one in, for example, in Hawaii, looking at the same object simultaneously. Then actually these actually can be described as the single dish of it can actually achieve the angular resolution that defined by the telescope of size of separated by these several 1,000 kilometers of diameter. So this is actually this is the concept, and it has been tried and then used multiple times, and this is known as very large baseline array. And imagine that actually we add the satellite, radio satellite, that actually sent to the 100,000 kilometers away from the Earth, and then the radio telescope can be actually used in the interferometry pattern. That actually now they're providing the effective the diameter size of several 100,000 kilometers that actually provide even that actually microarcsecond level of the angular resolution. So this is the concept of a very large baseline interferometry, so BLVI. So it has been actually that the suggested, but actually that has not been because of the expense and then cost issue. BLBA has been implemented and used in the many the scientific project. BLBI is actually still being actually designed and then they actively sought after. The more recently, several years ago, that actually that on the very dry desert on Chile, so above the 16,000 feet above the sea level, there we actually they put the 12 meter the radio dishes. 64 of them actually is arranged on the Atacama Desert. So this Atacama Desert, the array is actually known as ALMA. Okay. So this ALMA of 64 antennas actually can achieve the maximum baseline of 10 kilometer, and it is actually the operating in a the rather higher domain. So remember that actually radio frequency is actually the typical radio. The wavelengths start with the 0.5 millimeters, right? So that basically this Atacama is actually just tapping into the sub-millimeter the waves. So that actually it is operating in a rather higher frequency. So even for the relatively small maximum baseline, because it is operating at the higher frequency, it can actually achieve sub-arcsecond the angular resolution. Okay. So as you will see later on in the following slide, that actually when we talk about the different the astronomical sources, this ALMA array can actually can take the breathtaking pictures of the the fine structure of the forming planetary systems, for example. So because I think, as I mentioned, that actually there's the compared to the solid mirror, that actually we are actually sampling the reflecting surface on a few cases, and this solid mirror is actually mapping into the perfect the airy pattern, right? And then this the partially filled primary, I think, mirror reflecting surface will produce very poor dirty the point spread function, right? So this the coverage of the reflecting surface is recognized, and then how much fraction of the reflecting surface is covered in the PSF, the point spread function, is actually closely related to the UV plane. So UV plane is basically the we can actually recognize it as the two-dimensional the sky image is actually mapped into the kind of Fourier transformed the domain of UV plane. So that actually in this plane of sky, that solid circle is actually turning into the really into the so in a sense that actually if the UV plane is 100% actually just covered, then what we will see in the real 2D images, we will see the perfect airy pattern. So the larger the coverage at the UV plane, we actually get the fuller, more the fully surveyed the point spread function in the real sky domain. So the plane coverage will actually dictate how reliable that actually our final the image construction can be. Okay, so these are the several the examples, and then this is the I believe that this is the BLA observation. Okay, so that actually each individual the pass in the individual section is defined by the coverage of the individual pairs of the BLA of the telescope, and as you can see that actually it is actually reasonably covering the UV space, so that actually this much of actually the UV coverage can actually produce really fairly close that actually the airy ring like diffractions the structure, but still that actually there is some missing gap is contributing to some noise the structure here and there, right? Imagine that actually we see more the coverage, more full coverage of UV. So this is UV coverage of one radio observation. Then we can actually see that actually we're getting close to the more and more like the full airy ring, like the diffraction, the structure. And this is more like a typical the construction of the radio array observation. So that actually we see that actually that at the center we actually see achieving good high resolution, but actually that a lot of that actually just noise is actually are introduced because of the less than perfect UV coverage. So that actually that the point spread function from the array interferometric radio, the observation is oftentimes described as the dirty beam. So this is the diffraction pattern of the radio, the telescope array, and the projection onto the sky. So the image, the construction from this study, I think the images actually, we need to actually somehow decompose, because these many of these structures are actually because of the dirty beam UV coverage. So that actual the structure of the true celestial sphere, celestial source on the sky plane will be different from this telescope dirty beam the images. So what is being actually the thing is, if this is the true object, okay, on the celestial sphere, two binary stars, and somehow that actually our the radio observation is producing the point spread function of this structure, then each one of pixel is actually basically mapped, the filter through this PSF structure. So if we observe this with this PSF structure, then we will see this. Okay? Adding noise is actually, then we will see this is actually kind of just the dirty beam structure. Deconvolution is actually from this, the observed image. By using this known PSF information, how do you actually go back to this guy? So basically through the inverse, the Fourier transforms or not. So this is actually so-called the image deconvolution, and then radio telescope, for especially from the array or the observation, we will always have to actually do this image deconvolution by using this reproduce the PSF structure. So this PSF structure is decomposed with the final recorded image, then we can actually achieve recover the original or the celestial object images. Okay. So this wraps up the radio interferometry part, and in the following video, which will be released on the Thursday, then that we will actually talk about the various astronomical sources, and that actually they appear prominently, I think, in the radio frequency in the night sky.